Arguably the best feature of the software is the design mode. If you go to Solve, the Solve tab, click on it, you activate design mode by clicking on design. Before we discuss the design mode in more detail, it's a good idea to discuss the differences between the different solution modes. And that's the verification mode if you click on verify, the design mode, or the performance curves mode. The inputs to the verification mode and the performance curves mode are basically identical. In addition, for performance curve, you have to enter the inputs in this block as well. But we discuss both the verification mode and performance curves mode in two separate videos. In both verification mode and performance curves mode, the water outlet temperature is not known and it is calculated by the software. In design mode, the outlet water temperature is known because we want to design the cooling tower to meet a specific cooling load. So the water inlet temperature is known in all three modes, but with the design mode, the water outlet temperature is also known. And hence, the software is calculating the sizing of the cooling tower to meet the specific outlet water temperature. There are many different designs that can meet your design objectives, and that is the required water outlet temperature. You can increase the area of the cooling tower, you can increase the fill height. There are many parameters you can change to get to your design load. The software will calculate many possible designs that will meet the water outlet temperature that you specify here, based on the input settings that you define in these boxes. The software will calculate many different designs that will meet the water outlet temperature that you specify in this box. And it's doing that by changing the fill height. You enter a start fill height. There's a fill layer height. If you select the fill from the transfer areas box, it will populate the fill heights available for you, and you can specify how many layers the software will need to go to, and it will increase it one by one until it reaches those number of layers. A very important consideration in the design of cooling towers is the selection of the air loading and water loading and the ratio between them. So when you design it, you have to select an air loading and a water loading that is general or acceptable for those types of cooling towers. If you select the air loading that's too high, it might lead to very good transfer, but it will also cause very high pressure drops through the cooling tower, and it will require a lot of fan power. Now the software will calculate many different permutations, and then it is up to the user to select the possible design that will fit his conditions the closest. The solution mode or design mode that we've selected here is where LFI, that's the height of the fill, is known, and the airflow rate is unknown. It will loop through all of these scenarios for a specific water loading. For that water loading, for the fill height, for each permutation, it will calculate what should the airflow be to meet the water outlet temperature of 30 degrees in this case. As we go through an example a bit later, all of these things will hopefully become more apparent and clearer. So let's go through all the steps to set up a design. So we click on design, we look at our tower type, that's perfect. This is our design atmospheric conditions that we enter here. Under dimensions, we don't care about any dimensions because the cooling tower software will calculate that for us. But two dimensions are important to enter here, and that is the height of the spray zone and the height of the drift eliminator. So these two areas you have to specify, but all the other dimensions will be calculated by the software to meet that specific design load. Now these dimensional relationships are used by the design mode of the software to calculate the dimensions to meet a certain design load. And that is the ratio of H3 to the width of the cooling tower. Now, this is this ratio between these two dimensions. If we select it at 3, if you divide 12 by 4, it will give you that 3.3. So this is just to make sure that the height of the cooling tower inlet is proportionate to the width of the cooling tower. Then the next important one is the fan cover ratio, and that is to calculate the diameter of the fan. Then it is the height of the diffuser. In general, it's acceptable so that the height of the diffuser is 40% of the diameter of the fan. Then if you want a square cooling tower, it's the breadth divided by the width. If you want a rectangular cooling tower, you can change this dimension. Then it will not be a square cooling tower from the top view. And also the minimum plenum height. So the plenum height specified here is relatively high because in this specific design there's access needed to the plenum chamber for the drive system. So that is why it is selected to be relatively high. And then you also have to select the frontal area specification. You have to select the factor of 1. So it will use the full factor or the factor that you specify here. If you make this, let's say 0.96, it allows for 4% of the available area for full support and any other internals of the cooling tower. Also just note that you cannot use more than one fan in the design mode. It's only in verification mode that you'll specify the number of fans. Then you also need the operating conditions. You need the water flow rate at the inlet and the water inlet temperature. And very important, you have to put the air side on specify. Because in the design algorithm, it will use this specification to calculate the airflow rate. But don't worry about this input in design mode, because the software will calculate the required airflow temperature. If you don't select it in design mode, it will give you an error. So I'll put it back and you'll see the error that we'll get when we try to run the design. Then you also have to specify the model. Now please use the Merkle method in the model selection, because the popper takes very long time to run and it might take excessively long to run. Then you have to specify which transfer areas to include, and also what you have to specify is the fill type. The software will not select a fill for you. As a designer of the cooling tower, should specify that fill, because that fill might be available or for the specific water quality. So we select that. In this example, let's choose a fill. If we go to the fill type numbers, if you want to include, for argument's sake, a Brentwood fill, and let's pick in this design the shockwave, that is fill 64. We can either click on the arrow there, or we can just type in 64 here. If we type that in, you'll see it will change to the Brentwood. Now if we go to the solve tab from here, you'll see that it automatically updated the layer height of 0.3. If we go back to the transfer areas, we go back to the table, we can see that the fill is 300 millimeters or 0.3 meters as included in the table. If we select a different type, let's go to fill type 57. You'll see the interval is 100 here. 57. You can also override it. Of course, you don't have to enter it, but now you see that fill layer height, it automatically updated to 0.1. So let's use the shockwave design here, that is fill 64. We also have to, for design mode, define all the pressure losses that are included. Very important, if you selected a fill type from this database, you also have to update it under empirically on fill loss coefficient. You have to say use database. If you don't do it, it will also warn you. It's not an error, it will warn you in the warnings when you check the inputs. The fan specification is not activated during design mode because you have to select the fan by looking at the outputs. So in design mode, ignore the fan tab. All the controls are also relevant, from the solution tolerances to the initial conditions and the relaxation parameters. They are all applicable. And then you go to solve and you can click solve. But before we click solve, we can just look at the inputs. So let's go to check inputs. And if we go to the info tab, it will give us the results of the input checks. So you also hear a little error sound, and you can see operating conditions, S side needs to be set to specify. So if we go back to the operating conditions and we click that to specify, we go back to solve, and now we check the inputs again. Hopefully this error will then disappear, and you see that error disappeared. But there's still a warning present, and that is fill database is not selected for KFI, but for the Merkle number. So we go to pressure losses, and here we just say use database. Go back to solve, go to the solution setup, and now we're going to press solve. The last decision we need to make is the values of the air loading. We will start at 1. You can select any interval and it will stop at that interval. So it's by default 1 to 5. Those are the generally accepted values for cooling towers. Values between 1 and 5. Obviously it can go higher, it can be lower, but that is what's acceptable. Just to shorten the execution time, we can make the interval 1. So it will start at 1, then 2, 3, 4 and 5. And for each of those water loadings, it will start at the fill height. Here it already populated the fill layer height, and we can start at 0.3. So the first layer will actually be 600 millimeters or 0.6 meters because it already started at 0.3. Then it will add 4 layers one by one and calculate the required airflow through the cooling tower to meet these specific water loadings that we've selected. The outputs will be shown in here. So if we select the solve button, we click on solve, the residual and the other tab will disappear because they are not relevant for the design mode, only for verification mode. And if we go to input, it will show us how the solution is progressing. It will also run the input check, and it will tell us solution started for the design process, and it will also state that no detailed iteration info is presented in design mode. Only in verification mode does it give you details about the iterations. And it will show you, as in the performance curve mode, it will show you the progress. And this will take a while to run, and we'll discuss the results when it's finished. So it concluded the design process, and it actually took relatively quickly because it is using parallel computing. So it shows the progress after 25% completion. It took 1 minute, but this is just an estimation. It is rounded to the closest minute or the nearest minute, and in the end it took less than 3 minutes to run. Now if you go to the solution setup, it will give us the output in graphical output form, So here is the calculated airflow rate through the cooling tower for these water loadings that we've selected, and it calculated the size of the cooling tower where the outlet water temperature is 30 degrees within a very close tolerance. So all of these cooling towers stated here can work, and now it's up to the designer of the cooling tower to decide which of these to use. And the most important step here is then the specification of the fan. And generally, when you specify a fan, the fan curves available, it's the pressure drop that you have to specify, or that you have to know, the volume flow rate in cubic meters per second, and it also gives you the density of the air at that point. So using the volume flow rate and the pressure drop, you can then find a fan and specify a fan that will give you that duty. So we can also look at this in graphical format. So if you click on graphical output, it shows us on the axis of, on the vertical axis, the pressure drop, on the horizontal axis, the volume flow rate, and for every fill height that we've selected, so it started at 0.6, it only looks at 4 instances like we've mentioned, and so 0.6 meters, 0.9, 1.2 and 1.5. So if you look at the 1.5 meter fill height, you can see that it requires the least amount of volume flow rate, and the pressure drop changes from 25 pascals all the way up to 400, and it just gives us all points what those cooling towers, or what the width of the cooling tower at that point is. So if we go back to the table, now we can select the cooling tower. So we can also pick one here, and we can sort these columns. So if you click on it, we can sort them. If you click on it again, it can sort from the highest to the lowest, sort again original, and then from the lowest to the highest. So if we want a cooling tower with the smallest width, because the real estate available for the cooling tower is very critical, we can click on this one, we say select, and now we can say pick design. If we say pick design and we go to the dimensions, we'll see that this is that cooling tower that it calculated based on all of these dimensional relationships. So the minimum plenum height is 2.9, you can see it's 2.9 here, and it's an 18-foot fan, and we know that it's the closest to a fan cover ratio of 0.4. So this is the cooling tower that we've selected, or that was the design, and now we want to verify, does this cooling tower actually give us a water outlet temperature of 30? Now we can go to solve again, and we can click on the verification mode, and now we can say solve. So now 2 tabs will reappear here. So those are the residuals and the parameter values. The other graphs are not available because we've selected the airflow rate. It's not calculated with the fan, and okay, it converged. Now if we go to the outputs and we wait for the table to update, you see the water outlet temperature is within a very close tolerance of 30 degrees. Now we can go back. If you're not happy with that for whatever reason, we can go to the solve tab, go to the solution setup. Let's just, for argument's sake, look at the different fan, the one with the widest width. But now for that one, you can see that the fill depth is only 0.6 now, so that is the lowest fill depth that we've selected. We say pick design, we go to dimensions, it will update, and you say, okay, but this cooling tower doesn't feel right, the rain zone inlet is too high, it's a very thin fill depth, and it requires a huge fan diameter. But this cooling tower will meet the design output duty of that 30 degrees Celsius that we've selected. If we go back to the output table, you would have noticed that for the air loading, the water loading, and the ratio of the water to air loadings are color coded. Now, these are color coded according to recommended values that is published in a publication, and it's also, you can also see those recommended ranges here. After we've run the verification, in the end it will just give you the recommended water and air loadings, and based on these ranges, these are color coded according to that. So if we go back to the solution setup, so if it's dark green, it means that that's within that range, but it's also acceptable if it's outside that. So for GA, you see that it's from 1 to 2, it is green, and if it's more than 2, it is light green. So if we go back to the info here, we go to the, you'll see that between 0.5 actually and less than 2.44 to a maximum of 5. So if it's outside this range or inside this range, it's light green, but all the way to a max 5. If it's more than that, there will be no color code. It can still obviously work, but it's not recommended according to these. But as a designer, you are also welcome to use it outside those. If the fills were tested outside those ranges and it's working, then by all means that is acceptable. But this is just a visual guide to guide you picking a design where the water loading and air loading and the ratio between them is acceptable. After looking at the design, and I wasn't happy with certain things, so for argument's sake, I want this minimum plenum height to be only 2.1 meter. I also want this ratio between the air inlet and the width of the cooling tower. That's too high for me. I can also make that 0.25. And I also want to look at various different airflow velocities and fill layer heights. So I can go my end water loading here, I can go that all the way up to 7, and I even want to look at intervals of 0.5. So now it will do a lot more calculations, and I will do even fill layers up to 6 different fill layers. And now if I click then on design and I click solve, the design and parameter value tabs will disappear. On the info, it will show me the input checks, all of those are fine, and now we can wait for the solution to take place. The design algorithm took like 7 minutes, just more than 7 minutes, and running through all the different permutations. If we go to solution setup, you can see in the table now there are many more possible designs of the cooling tower, and you also can see the color coding. If it's no color, it's outside of the recommended range that I mentioned earlier. You can also use the columns to sort them. So if I want to look at the cooling tower with the smallest width, I can just sort it, click it until it's sorted. So if I can click on that one, now it's all outside of the ranges, and the pressure drop is excessive. So if I say pick design and I go to dimensions, that is design of the cooling tower with all these dimensional relationships applicable. Now the fan is relatively small, and it's a very thick fill height. Now you can use this to find a suitable fan. So you can also click export to Excel, and you can have formulas that calculate the operational cost and the construction cost for you. And you can optimize according to that. But here are some parameters that will help you to pick a design: the fill volume, the diameter of the fan in meters and in feet, the inlet height, the height of the cooling tower, the total height. So you can use this table to find a design that's suitable. With the pressure drop and the fan power requirements that it needs, and also you can use this to find a design. If we click on this one, for example, where all the values are green, if you look at the pressure drop, is also I think acceptable there. So if we click on that one and we say pick design, now it will give an error because we've already picked a design. You'll see only one solution can be selected. So you just say OK, and you deselect the previous one we've selected. Click on that one, say pick design, and now if we look at the dimensions, it will soon change to the new one. Just give it a time, and this is the same output was achieved by this cooling tower as all the other towers given in this table. So the final step of the optimization requires the user's input, because we cannot incorporate everything into the software. So if you use the pressure drop, the volume flow rate, you can specify a fan. If you specify a fan using these three parameters, usually you require the operating point in terms of the volume flow rate, the pressure drop, and the density of the air at that point. Then you can get the characteristic curve. You can enter the characteristic curve into the fan tab, and then if you rerun it, you can see if you get the same operating point as predicted by using the fan curve as well in verification mode. We can also view the outputs in graphical format. If we click on the graphical output tab, we can see a curve for every fill height that we've selected in this design settings here, and every point represents a cooling tower that will achieve the water outlet temperature, but with a different width, with a different fill height, and all those different dimensions that are determined by the dimensional relationships. You can see that it's not necessarily a smooth curve for everyone, because not all the inputs are necessarily continuous. So the fan diameters, for instance, go to the nearest diameter in feet. So you can see here, if you want to view the different options, what does it mean for the different fill height. You can see if a fill height is only 0.6 meters, you can see that you require a very high volume flow rate to meet the water outlet temperature, and with the corresponding pressure drops necessary through the system. So the point here requires a fan of 18 feet. It gives us the air loading, the water loading, the ratio, and then the width of the cooling tower. If you cannot see it, you can click on the screen and you can just drag it across, and you can just see those values. Here at the bottom, the fan diameter is 48 feet and the width of the cooling tower is a lot more, but now you require a lot less airflow through the cooling tower, so the air loading is only 1, the water loading only 1, and that ratio. So all of these represents cooling towers that can do the job, and it's up to the user to decide which one is the best with regards to the area that's available, the real estate available, also the fan power requirements. So if it's not a problem, you can select a very small tower and with a small footprint, but then it will necessarily have then a thicker fill height. So it's a bit of trial and error finding the right design, but all of these designs will meet the required design load.